Welcome back. I hope everyone is ready for more quantum field theory. Merzuk, take it away.
Okay, welcome to the second part of the Beyond DFT lecture, where we dive into the random phase approximation. Okay, let me first give you again a short overview. I will start with a reminder on the Hartree-Fock method. Afterwards, I show you how the ground state energy in quantum field theory is calculated using the random phase approximation. I will be discussing the RPA implementations in VASP and try to explain what happens under the hood, so to speak. Afterwards, I will demonstrate how to use the RPA in VASP to calculate the corresponding ground state energy. Finally, I will show you some results and discuss pros and cons of the method. I hope you like it. Okay, how is the total energy in quantum mechanics calculated? We have here the Schrödinger equation with the Hamiltonian on the left and the energy on the right we are looking for. So the Hamiltonian contains three terms. The first term is the kinetic term of the electrons. The second term is the ionic potential, so the potential that attracts the electrons. And the third term is the hard one. So this is the electronic repulsion term. Due to this term, we cannot solve the Schrödinger equation exactly. We have to rely on approximations. So one approximation is the Hartree ansatz for the wave function. So Hartree assumed that the wave function is a product of one electron orbitals, and these orbitals are nothing else than the solution of this one electron Schrödinger equation. So the Schrödinger equation for one electron without any interaction term between other electrons, which is somehow also clear. Okay, now within this approximation, the total energy of the system can be written as follows. So it contains three terms, the third one coming from the kinetic term, the second one coming from this ionic potential, also known as the external potential, and the third term is the Hartree term, which depends now on these Coulomb orbitals here. Now, the Hartree term captures the dominated contributions to the electronic repulsion term. However, there are still terms missing. For instance, the Pauli exclusion principle is not accounted for with the Hartree ansatz. That is, two electrons cannot be in the same state according to the Pauli principle. Now, following ansatz for the wave function, also known as the Slater determinant, accounts for this principle. Here again, the one electron orbitals from the Hartree method are used. However, now if two space coordinates, so if two electrons are at the same space, the corresponding wave function is zero. The Slater determinant yields one additional term to the total energy, and that is the exact exchange term, or the so-called Fock term. Nevertheless, there is still something missing, namely the term that comes from correlation effects. Now, how do we account for this missing piece? The main idea is to include more Slater determinants in the wave function. So Slater determinants that, besides from the one containing only occupied states, the ground state Slater determinant of the Hartree-Fock method, we include now also Slater determinants that have one electron that is unoccupied. So one electron that is above the Fermi energy, like in this picture here. So there are several possibilities for the singly excited Slater determinant. And similarly, we include also higher excited states, like depicted here on this picture. Now, one might insert this ansatz into the Schrödinger equation and diagonalize it, but this approach, known as configuration interaction, is exponentially hard. So there's a more convenient way to deal with these excitations. And yep, you guessed it, it's quantum field theory, which I'm going to discuss now. So in quantum field theory, one uses the so-called second quantization formalism. To understand what this formalism does, one first separates the Hamiltonian into two parts. So the first term is the non-interacting Hamiltonian, for which the ground state Slater determinant is known. And then the second term is the Coulomb interaction. And then we make two observations. So first observation is that the Slater determinants, including those with higher excited states, diagonalize the non-interacting part. So they are proportional to these one-electron energies. And the second observation is that if we evaluate the Coulomb interaction with these Slater determinants, the Coulomb integrals pop up. Now in the next step, one shifts the perspective and introduces the particle annihilation and the particle creation operators. Now, the idea here is that this operator, Ci, can annihilate electrons above the Fermi energy, while simultaneously can also create a hole below the Fermi energy, like so. And the conjugate operator, in contrast, does the opposite. So it creates an electron above the Fermi energy, so virtual electron above the Fermi energy, and a hole below the energy, the Fermi energy. Note these operators now act on the ground state, that is the Slater determinant, S naught, however, now in Fock space. So this Slater determinant in Fock space is characterized by the fact that it contains no electrons above the Fermi energy and no holes below the Fermi energy. So if you use this relation here, so acting on this ground state, you get 0. And also if you include these operator eigenrelations, you also account for the Pauli principle at the same time, which is quite neat. So far so good. So now the interacting ground state energy in quantum field theory is imagined as the state of all possible virtual fluctuations out of this ground state that vanish after a finite time. That is essentially, if we use again the language of diagrams, a sum of all closed diagrams that have, for instance, these forms here. As in the GW case, one only needs two ingredients to evaluate these diagrams as integrals. So we need the Coulomb interaction and we need this Feynman propagator, or the so-called free Green's function. So I'm repeating here, this function describes the free propagation of both an electron and a hole. And using this function, the number of diagrams that have to be accounted for is tremendously simplified and reduced. So that's because we only have to look at the topology of the diagram. However, we also have to account for the symmetry of a diagram, and how to do that is written in this really good book. Definitely a good read. Okay, so now Goldstone studied this expectation value for the total energy of the system we're looking for using these diagrams, and he found that this denominator cancels certain terms in the numerator if expands this separately in a perturbation series. And what he found is the so-called linked cluster theorem. So the linked cluster theorem states that the total energy of the interacting system is the sum of all connected diagrams. So disconnected pieces don't have to be taken into account. This is, again, simplifying the topic. And now we use, again, the most convenient way to split the total energy into the kinetic energy, the external potential energy, also the energy from, it means the energy from the ion-electron interaction. And we have here the Hartree term, which can be associated with this first diagram. The exchange term can be associated with this oyster diagram. And the correlation energy is now the remainder. So all other diagrams contribute to the correlation energy. That means all post-Hartree-Fock effects are included here. It turns out that for many systems, these ring diagrams here are dominating contributions. And if we consider only these bubble diagrams, one ends up with the famous random phase approximation. One can evaluate these diagrams up to infinite order, and one can even obtain a closed form for this. Now, let's see how to do that. The infinite series of bubble diagrams can be evaluated with the independent particle polarizability. So we have this particle polarizability in a matrix notation indicated by these brackets here. So this is a matrix that also has to be evaluated as a function of frequency, but this time in imaginary frequency. And similarly, the product with the Coulomb interaction in a matrix notation is simply this object here. Now, if you analyze the topology of these ring diagrams, you will end up with a contribution for the nth order term that looks like so. So it is simply the product raised, so this object raised to the nth power and divided by n. And if you are good with power series, you will immediately recognize that this is the logarithmic series for this matrix here. So you can essentially arrive at this final form for the RPA correlation energy that traces this matrix logarithm and integrates over the imaginary frequencies. In the following, I will be discussing how to evaluate this integral most efficiently. The simplest way to evaluate this correlation energy is to work in reciprocal space, because the Coulomb interaction in this space is diagonal. So that means that the product of this Coulomb matrix with the polarizability is done in this space, and we need the reciprocal version of the polarizability, which once again can be obtained from the direct calculation using the formula of Adler and Weiser. Next, we need to evaluate the eigenvalues of this matrix product. And we need to do this at every Q point for every frequency point. Now, the question is, how do we evaluate the frequency integral? Is evaluated with an integral quadrature. And these transition energies in the polarizability, it turns out, play an important role to determine the best integral quadrature for the RPA integral. Now, in the following, we discuss how this quadrature is determined. Consider the lowest order contribution to the RPA energy, which is known as the MP2 contribution. So this MP2 contribution is quadratic in the polarizability. That means quadratic in the eigenvalues, and the corresponding contribution to the integral will look like so. So now, interestingly, these eigenvalues have the same functional form than the polarizability, and you can evaluate this integral analytically and end with the explicit result, which shows you that the lowest order contribution is inverse proportional to the transition energies that appear in the polarizability. So now the best integral quadrature minimizes following error for each transition energy that can appear in the polarizability. So the idea is you approximate this integral by a quadrature. This is this sum. And then you subtract the exact value of the integral. And by minimizing this maximum error that can appear for every transition energy in the system, you end up with an integral quadrature. And this is the best integral quadrature that you can have. And in fact, it converges also exponentially with the number of frequency points you include when performing this integral. So it converges exponentially with the number of quadrature points. Now, the beauty about this approach is that it also works for higher order terms. So the reason is that this is the dominating contribution. Higher order terms are smaller and therefore have a smaller error. If we control the error of the lowest order, we control the error of all orders. And the following plot shows you now the convergence of the Minimax quadrature for two systems. We have here zinc oxide and silicon. And on the x-axis, we have the number of quadrature points. On the y-axis, we plot the absolute error of the RPA integral. And of interest to us are here these blue dots. And you see that they are decreasing exponentially with the number of frequency points. So increasing 2 points, increasing the quadrature by roughly 2 points gives you 1 additional digit, and so on in precision. Okay, how does an actual RPA calculation in VASP look like? In contrast to GW, here 4 steps are required because one has to calculate the exact exchange contribution. So in the first step, you start with a DFT calculation. Then you determine this exact exchange contribution with this setting. So you perform eigenvalue, but don't update the wavecar, and select Hartree-Fock. Then in the next step, you increase the virtual orbital space by using a large number for n bands, very similar to the GW approach. And you end up with a wavecar and a wave there if you select this L-optics. That is a preparatory step for the actual RPA calculation, which is done in the last step by selecting algo equal RPA. Here, n omega, the number of frequency points in the integral quadrature are given usually relatively small. So after the Hartree-Fock step, you should actually write down the energy in the outcar, since it corresponds to the first part of the total RPA energy. So you look into the outcar after the second step, and you pick this number to get the total energy for the exact exchange and the other terms. Now, after the RPA step, the outcar will contain a block of data that looks like so. So VASP actually calculates the RPA integral for a series of different cutoffs given here in this column. And it uses the corresponding RPA correlation energy values to extrapolate to infinite cutoff. So this infinite cutoff value, together with the energy of the exact exchange step, gives you the total energy of the random phase approximation. Now, what can you expect from the results? In fact, RPA has formidable lattice constants. This plot here shows the deviation of calculated lattice constants from experimental values for a series of systems, and this for 4 different methods. So for PBE, we have the triangles, so slightly larger band gaps compared to the experiment. Then LDA, which has smaller band, I'm not saying band gaps, sorry, lattice constants, of course. And the exact exchange of degree line, and then the RPA. Finally, the RPA values, they are really in between these 2 methods and are very close to experimental lattice constants. Here on the right-hand side, you see the relative error for a set of different systems for the lattice constants computed with different methods. And once again, RPA overall has a relatively small error. So far, so good, but how do RPA lattice constants for transition metals look like? So again, comparing RPA with methods like PBA soil or even van der Waals functionals like opt-B88, you see that overall the RPA values are not bad at all. So actually they're really good for heavy elements, like 4th, 5th row elements, but they're not that good for these light transition metals. Now, the reason for this is actually a finite basis set error, so which is not corrected for when we use standard GW potentials. So if we use norm conserving potentials, the agreement with the experiment is almost perfect. This is really comforting. So nevertheless, these norm conserving potentials have a large cutoff, and typically twice the cutoff of the standard potential. So this in some sense comes with a caveat. Now, one more thing about the results you can expect from RPA. This table here shows calculated heats of formations with respect to the normal state at ambient condition, given in kilojoule per mole, for a various set of different calculate methods. And is obtained simply by computing these two energies and then subtracting the energy of the compound. Now, here in the experimental column, you see the values of the corresponding heats of formation for the systems. And you really also see that PBE is really not good. So it's really far off from the experimental values. Likewise, LDA is maybe a little bit better, but still exact exchange might be better for certain systems, but overall RPA gives the best agreement with the experiment. So, and now this here connects to a question from the GW Q&A. So this is a topic where RPA shines. So the question is, how do absorption energies on metallic surfaces look like when using RPA? Here we have the results for the carbon monoxide absorption energy on platinum and rhodium 111 surface. And as you can see here on this plot, on the right-hand side, the experimental value for the absorption energy, which is the y-axis, versus the surface energy, which is the x-axis, is located here. So the experimental values are in this region. Now, regardless which DFT functional you choose, either PBE, meta GGA, or even hybrid functionals like HSC, you will never get out of such a straight line. So you always end up somewhere here, yeah. And similar for the rhodium surface. Now, RPA is the only method that can pull you out of this straight line towards the experiment. And that means that RPA is the only method that, studied here, that increases the surface energy and decreases the absorption energy at the same time. So the consequence is that the exact absorption location of the CO molecule can be predicted on the top side. Okay, so in summary, here we have more results. So on the right-hand side, you have the surface energy for a set of surfaces for different elements. And we have here the experiment, which is given by this yellow line. And you see that actually RPA is really close to the experiment. So does actually PBE Sol as well. So PBE Sol and RPA are really good for surface energies, while this blib functional shouldn't be used. Now comparing the lattice constants, again, blib is not great, and the relative error to experiment is the smallest for RPA. For PBE Sol is not that bad, but still, yeah. And here we have the absorption energy plotted compared to the experimental values, which are given by these error bars here. You once again see that the values of RPA are in best agreement. So in total, we have the right side preference, good absorption energies, we have excellent lattice constants, and we have good surface energies. Now, what about the band gaps, or let's say the LUMO and HOMO position? DSD does well for the metallic surface, but not for the CO molecule. So you see that actually the LUMO, the lowest unoccupied molecular orbital, is too close to the Fermi energy, which is here 0. And the experimental value would be somewhere here. Now, if you consider the hybrid functional here, it does well for the CO, but not for the surface. That is, the d metal bandwidth is too large. And GW in contrast gives a good description. Let's look at the computational bottlenecks that you can expect using the RPA implementations in VASP. So the presented implementation, that is the direct calculation of this polarizability, is fast for small systems, but slow for large ones. And it scales with the fourth size of the system, with the fourth power of the system size, and also quadratically in the K points. Now, this is restricted to relatively small systems and can therefore not be used, for instance, for the computation of defect formation energies. So the question is now, how do we accelerate this algorithm? How do we reduce the scaling? In fact, what I've presented you so far was was only the last step in the low scaling RPA approach. So the evaluation of the RPA integral. The idea is to use Green's functions in imaginary time to reduce the scaling to cubic in system size. So in the low scaling RPA approach, we start with the Green's function in real space and imaginary time. Also to build the polarizability in the same domain using this equation, the dominating step. Usually we set up this function in reciprocal space, but this is not important now. Important is that this is actually relatively easily done. Then we need to transform this polarizability in space-time into the reciprocal space and imaginary frequency domain. So this is done in 2 steps. The first step is performing the transformation to reciprocal space using an FFT, which is done on a uniform grid. And there, this function is stored. Now, these matrices are large, and one cannot store them on hundreds of imaginary time points to perform the Fourier transform to imaginary frequency. The hard part here is now to find a compressed representation of this object on the imaginary time axis that allows for 2 things, namely for an accurate transformation to the frequency domain, and these frequency points should then be used for the integration of the correlation energy. So in some sense, we require a dual imaginary time grid for the Minimax quadrature points, because we know the quadrature points are the best points to evaluate this integral, so we need the time points, the corresponding ones. To obtain this imaginary time grid, we first inspect the functional form of the polarizability in imaginary time. So this imaginary time dependence is given by this exponential, where delta is a positive transition energy in the polarizability, any transition energy, but it's positive. And next we proceed in the same way as for the imaginary frequencies and compute the MP2 contribution to the energy, but this time in imaginary time. Note that this integral goes over positive times here only. And then you end up with the explicit form for this contribution, which of course is again the same as for the frequency one, namely 1 over the transition energy delta. And now to obtain the time grid, we again minimize the quadrature error now in imaginary time. Okay, so we solve this minimization problem, and this will give you an optimum time grid to evaluate this integral. Now the question is, why are these points here, the tau k's, a good choice for the Fourier transform, for the discrete Fourier transform? The reason for this is that the 2 Minimax solutions, the one for the frequency and the one for the time domain, span 2 almost isometric subspaces. So that is, if one represents chi on the Minimax time grid, the best frequency grid for the discrete Fourier transform is the Minimax frequency grid. So this plot here shows you how the error in chi looks like on the imaginary frequency axis when you calculate it from the Minimax time representation. So you perform this transformation and then look at the error, and you will see that the Minimax points have the smallest error. And this is a result from Minimax isometry, which you actually can read more about in this paper. And insofar, it's important because this method can also be used for finite temperature formalism of RPA. It's actually a general result. Okay, so how does an actual low scaling RPA calculation in VASP looks like? It is a 3-step procedure and simpler than the quartic scaling algorithm I have presented you before. The reason is that the exact exchange step is not required explicitly anymore. So it's done here in the 3rd step automatically. And like in the GW calculations, the RPA calculation in VASP is a 3-step procedure. So start with a DFT ground state. Is followed by increasing the virtual space with a large number of n-bands, perform an exact diagonalization for this large space, and then you use this as an input for the actual RPA calculation, which is done in this third step. So to select the low scaling algorithm, RPA R should be set, or ACFTT R. And again, a small number of points is sufficient due to the Minimax isometry. VASP writes now also the same block as in the quartic scaling RPA implementation for the correlation energy. This is not shown here, but what's really interesting or typically interesting for you is the total energy, and this is written in this line here. So this line contains the exact exchange contribution to the total energy plus the correlation energy in the random phase approximation, where one uses the extrapolated results of the RPA integral. So also, if you do all calculations in the PBE basis, like presented here, you may want to study the effects of these terms here. So these terms in the total energy are only zero if you start from a self-consistent Hartree-Fock calculation. Then these terms will be zero. But if you start from PBE or another functional, you will have some additional contributions to the total energies, which you can take into account for separately if you want so. Now, here you see some benchmarks for this algorithm that allows for relatively large RPA calculations. So, for instance, unit cells of 200 atoms on the gamma point or on 2K points can be simulated within 1 hour on 128 cores. And the algorithm scales linearly with the number of K points. So here on the x-axis, you have the K points. On the y-axis, you have the CPU wall clock time. And different lattice, different unit cells, and you see that there is almost linear scaling. Using this implementation, we have studied defect formation energies in silicon. Here you see the formation energies for 4 different vacancies using PBE, HSC, HSC plus van der Waals. This is an extended HSC method, which includes van der Waals interactions from this paper here. And we have quantum Monte Carlo results, which can be seen as some kind of reference. And the vacancies are given here by these pictures, taken also from the PRL here. The RPA results of VASP are given in this last column, and are actually really in good agreement with the QMCs. And once again, this demonstrates that van der Waals effects are captured well within RPA, including other bonding types. Now the formalism, however, breaks down for metals. So because already the lowest order term diverges if the band gap goes to 0. So the lowest order term is inverse proportional to the band gap, and you see if the band gap goes to 0, the contribution is infinite. Now, the best way to deal with this is to switch on temperature. That is to consider quantum field theory using the Matsubara formalism. And if you do so, you will see that the first non-vanishing contribution is actually inverse proportional to the time. I mean, those contributions coming from 0 band gaps, so metallic contributions. Now, this formalism can be selected in VASP with these 2 tags here. So actually with finite temperature, true selects the finite temperature formalism, and ISMU -1 forces the occupancies to be Fermi functions, which is of importance for this formalism. Other occupancies do not work. However, what works is the Minimax isometry. That still possible to use that. And here is a demonstration of the grid convergence for the corresponding finite temperature grids. So the green line here on the left-hand side gives you the grid convergence when using the conventional Matsubara grid. So this is the grid that is taught in textbooks when considering finite temperature perturbation theory. And on the x-axis, you see actually that we are plotting the number of points logarithmically. So in essence, this method is a pathological method. You cannot use it in reality. So the accuracy is really, the precision is really bad. However, this block here of data is the grid convergence of an improved method that goes back to Ozaki. And this method is insofar nice because it, first of all, accelerates the grid convergence, but also uses, instead of a discrete grid, like in the Matsubara grid, it uses a non-uniform grid. And our results here are obtained from the Minimax isometry method grid. So if you use the compressed Matsubara grid that we propose in this paper, you're having basically the best convergence that is possible. And you see also that the thick lines, which correspond to hot temperatures, that they converge always faster than the cold grids. Now here on the right-hand side, you see the grid convergence for strontium vanadate. So it's kind of a metal in DFT if you don't switch on, if you don't do anything else. And there are different choices for the temperature. And again, the warmest grid or the warmest temperature converges faster than colder ones. To perform finite temperature RPA calculations, again, a 3-step procedure is used. So actually everything is the same, except that you have to select Fermi functions, maybe increase a little bit sigma, but we have tested the algorithm that goes down to sigma equal a tenth of this value. Why is this important? It's insofar important that the temperature here is given in electron volt. So a sigma of 1 would correspond to 11 kilo Kelvin. So this here corresponds therefore to a temperature of roughly 1000 Kelvin. In the second step, you, however, omit now the L-optics tag. So you will not write a wave-delta function. Yeah, this is important because for metals, it doesn't help anyway. And in the third step, you perform the actual RPA calculation at finite temperature, but you switch it on with this tag. Everything else actually stays the same. And as always, test. So for metals, as I said, the K-point convergence can be difficult. And usually I suggest to drop the wave-delta file, so to not use L-optics in the second step. However, this means that you will probably have to increase the K-point sampling. Then you have to check, of course, the GW cutoff for the response function, so for the polarizability. That usually converges faster than the orbitals, which are this EN cutoff. However, I would say the default value is not that bad in most cases. And maybe you want to look into the number of frequency and imaginary time points with n omega. Yeah, and what's important is to mention is that the memory requirement for this approach can be large. And however, you can tweak it with this tag n tau par. So if you set n tau par equal 1, VASP will use the smallest amount of RAM possible for a system with a given number of MPI ranks. However, it will also slow compared to the highest possible value, which is n omega, which uses the largest amount of RAM, but is therefore fast. However, if you're running calculations on one single node and the node belongs to you, so to say, you usually don't have to set n tau par because VASP will estimate the optimum memory requirement from the Linux kernel. Good. So as a fazit, we have well-balanced total energy expressions that capture all types of bondings equally well. So we have metallic bonding, covalent bonding, ionic, and even van der Waals bonding. However, RPA is not chemical accurate. So there are still better methods which are more accurate, like for instance, coupled cluster. However, it's definitely an improvement over hybrid functionals and DFTs. Also, metals should be studied with the finite temperature formalism. So now time for questions.
Thank you very much. really from starting from the grounds up with second quantization and going all the way again. Yeah, I was wondering so everyone is invited, of course, to ask questions in the Q&A window. You defined correlation for us at the beginning of your talk. Maybe you could elaborate a bit on that, because this is such an important concept that we already met on the first day when Martin said that we basically met a map onto an uncorrelated system. So maybe you could explain what is correlation.
So an uncorrelated system that is probably the easiest one is the Hartree one, right? So if you assume the wave function has this ansatz, then you can solve this system, the Schrödinger equation exactly. However, you don't account for the Pauli principle, neither the correlation. So the next step, again, is Hartree-Fock. And I personally learned what correlation is in terms of Hartree-Fock. So Georg actually told me correlation effects are everything that is not Hartree-Fock. So if you do, for instance, if you study the helium atom, so you have 2 electrons, right? Already Hartree-Fock will not give you the correct answer. And you will see the missing piece comes from electrons that are not in the S states, so that are actually unoccupied. And it's actually quite crazy if you think about this. So even the most simple system like helium, you cannot describe it, because if you freeze one electron close to one state, the other one has to be everywhere. And this is how I actually understand correlation. So the case that you cannot have a one particle picture. However, you can account for approximately by mapping it to, for instance, this uncorrelated space, this Kohn-Sham space, but of course with approximations.
Mm-hmm, mm-hmm. So in RPA, to what level are correlations then? Or I mean, okay, to the level of RPA, but what does that entail to have correlation and effects included up to the level of RPA?
That entails that if you consider now this exact ansatz for the wave function and include excited states in your consideration, in RPA you would include only those states where the electron hole densities interact with each other. So you don't have the interaction between the particles, but the densities. So it's kind of an independent density approximation for the virtual particles. That's how I actually somehow see it. But of course, there might be others who think that this is not a nice description. But in fact, if you look at these diagrams here, such a point, you see you have an incoming and an outgoing propagator line. And this point here alone here corresponds to a density, right? And you have here kind of an interaction between densities. And that's what this diagram here is about.
So if I want to use this RPA, so a random phase approximation, then what is the realistic size of the system that I could relax to get, because you showed us this nice graph of how the lattice constant is perfectly estimated.
Yes.
What is the realistic size?
So the realistic size, so the largest lattice size I have studied for a single shot RPA calculation, let me pull that up, is about 200 atoms in a cell. So actually 250, but on a gamma point only. This is a single point calculation that takes time, right? So however, if you want to relax the system, so you want to relax the ions, you could do this with finite differences, which if the cell becomes large, this is actually really, it's madness to do it. I wouldn't do it, So realistically, it depends. If you want to use finite differences, you anyway stuck to small systems, because otherwise the degrees of freedoms become really crazy, too large. However, we have also actually RPA forces included in the code, which allows you to calculate the forces acting on the ions, but that is scaling again, I would say, by a factor of 4 more than RPA, single point calculations. And also it's still in development, and that's why I don't want to talk about it that much. But realistically, it depends. If you only have 1 degree of freedom, you can use definitely such large unit cells, yeah, because you can do finite differences. But if you can do finite differences, if you have too many degrees of freedom, this method is probably not for you. And what we did here, for instance, in this defect calculation is that we did the relaxation. So we removed we created a vacancy of the perfect crystal and then relaxed the structure using PBE. And on top of these structures, we actually calculated RPA. So what RPA is actually not bad is if you consider it as a post-processing method to PBE. So you do the relaxations and similar things with PBE and then do RPA on top of it. That's actually also how these, yeah. So I hope that this helps.
For this study on the defect formation, could you explain a little why QMC is a good reference as a comparison here?
QMC can probably considered to be the method that's giving you the exact total energy, because it solves the many body problem statistically, however, exactly. So you have a statistical error. Nevertheless, you don't neglect any correlation effects if you run the simulation for a very long time. And that's why we are looking at it as a reference. Of course, I don't know exactly how these calculations have been done now, and I personally can't do it. So yeah, actually, it's maybe a good question, yeah, for these authors.
Yeah, I mean, you have the reference there, so it's clearly can be looked up what exactly they implemented. I think there are so many variants of quantum Monte Carlo out there.
That's true. Yeah. But even if you consider this HSC plus van der Waals corrections from Tachenko and Gao, they are probably up before we published our results. They were probably the most accurate or most enhanced DFT studies on this subject, and the numbers are really, really very similar. So, yeah.
There's another question. So are the RPA results sensitive to the starting wave function? So GGA versus hybrid functionals, for example.
Yes, it definitely makes a difference if you start from PBE or Hartree-Fock. As an example, look, for instance, this here. As I said, if you start from Hartree-Fock, then this contribution will be 0. While in PBE, you have actually these contributions. And therefore, of course, also the result of the ring diagrams will be different. All in all, I would say experience shows that the best starting point is PBE and then RPA. So I'm not aware of people doing HSC and then PBE or something like this. So if probably people have done that, but I don't know if it was successful.
And would it be reasonable to use PBE to do the relaxation and a higher level method to do further calculations?
Yes, exactly. That's exactly what we did, yeah, for the defect calculation. So we did PBE to relax, and then did top of that single point RPA calculations. So.
And then where would you, how about the forces?
The forces, yeah, I don't know now exactly what's meant by this. So what the forces, for example, be integrated. So the idea is that if you use the relaxed PBE structure and then try to relaxed it again, but with RPA if the structure would differ, right? We have tried this for, I think, diamond, carbon, and there was really not a big difference. So PBE is really not that bad in giving relaxed structures. So that might at first contradict to the transition metal lattice constants and so on, but so in our experience, I haven't seen a big difference for those systems that we can do with finite differences relaxation.
So that might be surprising for people that suddenly we talk about temperature here, because before all the DFT there was zero temperature method. Okay, with the molecular dynamics part we already introduced a bit of temperature, but very different one. So
yes.
Could you explain how temperature enters the theory and
okay.
what?
So the idea here is that you can approach this diagrammatic series of the total energy from two sides. So you can consider the system at zero temperature, for instance, and if you do so, you study the total energy. Now, if you want to switch on temperature, what that means is that you consider actually kind of ensemble averages, and there you would not study the total energy, but more the, for instance, grand potential. Why is this the grand potential? The grand potential is used because at first you have to account for a heat bath, and you also have to allow for a particle number fluctuation. And this is given by the grand potential. So, and the grand potential would then
being the
virtual
electrons.
part. Yeah, but actually in that case, the particle fluctuations of the quantum field. And on average, you conserve the electronic number in the unit cell. So if that's not converged, or if that's not conserved, then you're doing something wrong. So this is actually also a problem in self-consistent GW, where you have to adjust the Fermi, which is actually then the chemical potential. And that chemical potential has to be shifted such that the number of electrons in a unit cell is constant. So now I actually forget about what I wanted to say. Yeah, so about the finite temperature. So the grand potential takes then the place of the total energy. And for that, you can derive a same perturbation series as for the total energy, but it's best formulated in imaginary time. So you don't consider it at real times, but you make a kind of a Wick rotation. So you map the system onto the imaginary time axis, and then you will see that there these correlation functions like the polarizability or the Green's function, they will have actually a periodic dependence or anti-periodic dependence on this imaginary time. And the period is basically given by the inverse temperature. And this is how this Matsubara formalism looks like or works. So it's really a nice formalism. So maybe I have some slides for this. No, I don't have, sorry.
Yeah, but maybe you can show that one again with the caveats from metals, where you showed the temperature dependence. I find it really intriguing that many times we computed the ground state because that is the only like accessible ground state and where theory could be solved. But now you show how going to a finite temperature formalism can solve a problem that would not be solvable at zero temperature.
Yeah, the reason for this is actually explained really well in this paper. It's a very short paper, I think 3 pages. And it shows you that if you use the zero temperature formalism, your occupancies, so your occupancy functions are theta functions, so they're step functions, right? So, and when you then perform derivatives on top of them, you get with really messy things, you get some distributions, it's product of distributions, and all this mathematical formalism doesn't work. Maybe you remember the products of so delta squared, if delta is the distribution, the Dirac distribution is actually not defined. And this is where actually the problems relies. Yeah. However, if you switch on temperature first, so you have kind of this statistical ensemble average, and then look at expectation values like the total energy, or in this sense, actually the grand potential, you don't encounter this problem at all because the occupancies are Fermi functions. These are smooth functions. They will never have any problem when you derive them, make a derivative of them. You can do that as often as possible. So you're always on the safe side. And Luttinger and Krohn, they actually proposed to perform the thermodynamic limit after you have switched on the perturbation. So you perform it afterwards. Not, you don't perform first the thermodynamic limit and then consider perturbation theory, but the vice versa. And that's why. Sorry, I just found a question here. Martijn actually asks this question here.
Yeah, maybe he can voice it out.
Yeah, that would be great.
Can you hear me?
Yes, we can.
Yeah, so I was, of course, this question does not come completely out of the blue, but maybe you could comment on possibilities to make RPA and the forces you can compute for it into a practical method for larger systems in the context of machine learning.
Yes, thank you, Martijn, for pointing this out. That is actually something that is on the agenda right now. So with the RPA forces that are available actually in VASP, we could calculate the forces and train a force field with the machine learning code, very actually analogously to the PBE-MDs, and then end up with force field that captures energies and forces of the RPA well. So with that, we could actually scale to really large systems, and that's something that we are aiming for. So, but it will take time to get there. Thanks again, Martijn.
Yeah, I think everyone who experienced the speed up that machine learning force fields could bring is now really excited about seeing machine learning also speed up this this calculation.
Yeah, this would be really great. One more point maybe for tomorrow, don't use the low scaling approach if you share the node. Okay, I forget about mention this in the talk, but the reason is that this algorithm is really greedy concerning memory. So it will just use the memory for your run and let the others starve, so to say.
So thank you very much, Merzuk, for this great introduction to RPA. Thank you.
Okay, bye-bye.